We begin now our study of electromagnetism. We begin with static electricity and static magnetism. Static electricity means we won't be dealing with electric currents, except maybe brief, very quick currents where static electricity is transferred. And any magnets we talk about will not be rotating or moving around. Now, the knowledge about electricity and magnetism dates back at least to the Greeks. The word electricity comes from the Greek word electron, which was their word for amber, fossilized tree resin, because it was known to them that if you rub amber with various things, you can it will exhibit these symptoms that we nowadays attribute to static electricity. But there was a renaissance. I mean, most of our modern knowledge of the detailed knowledge of electricity and magnetism that we have came much later. This guy Gilbert, in the latter part of the Renaissance, the literal historical Renaissance, he did work on static and electricity and magnetism, and had a model of the Earth. Has had a globe with a magnet in it, in which he did experiments and compared with observations to conclude that the Earth was a giant magnet. Then, of course, we have people like Benjamin Franklin with his experiments primarily in static electricity. Now, here, these names you see here are, of course, not the only people that were working on this, but we will be talking about these names. One name that is missing, unfortunately, is that of Maxwell. James Clerk Maxwell was born about 40 years after Michael Faraday, there at the top. And he pretty much is credited with bringing it all together and producing a single, coherent theory, though there was further progress made, of course, after Maxwell. So here's the basic fact of static electricity, or what we now call static electricity. If you take two objects and rub them together, it often happens that they exhibit attractive and repulsive forces. The ancients, the Greeks, used amber, glass rod, that we find convenient nowadays. If you rub a glass rod with silk, then you will find that the glass rod is attracted to the silk. And if you take another glass rod that has been rubbed with silk, you'll find that it repels, that such glass rods repel each other. And furthermore, two pieces of silk that have been used to rub on glass rods, those silk handkerchiefs will, in fact, repel each other. We will use this electrometer to investigate two different charges. One will produce on a glass rod, and a charge that we will produce on a black plastic rod. So we'll rub the glass rod with a cloth, an artificial cloth of some kind, and we'll touch. You can see the deflection of the needle. So we touched and evidently succeeded in transferring charge. Now, what happens if we bring that same kind of charge up to the, if we bring the same kind of charge up, the glass rod charge, it deflects even more, right, which we can, there. So there's been no charge transfer just by bringing it up close, but we can detect that it's the same kind of charge. Now we'll take this black rod and the skin of a dead rabbit or cat or something. Now we could see this black rod charge is different. This is a different kind of charge than the glass rod charge. let's see what kind of charge is produced by the Van de Graaff. What kind of charge is on there? Let's just give it a quick, it's probably enough. You can see the induced charge separation. Ooh, that was a snap. I'm going to discharge. All right, but there is still this guy. All right, I heard a bit of a snap. Yes, so we transferred some charge from the Van de Graaff to the electrometer using this. I've discharged them all, so this large sphere. All right, so let us check. Is this black rod charge or glass rod charge? Oh, it does not look to be like black rod charge. Let's make sure. Yes, this is definitely acting like glass rod charge. So the Van de Graaff evidently is producing glass rod type charge. We say that the objects are charged, and since like objects repel each other, we suppose that objects with like charge repel each other. The Latin having to do with glass, that word in Latin is vitreous. So the charge on the glass was originally called vitreous. And the charge on the silk was called resinous, where resin referred to the amber, which amber, as it turned out, more often than not, for most objects, it takes on the same charge as the silk. So now with Benjamin Franklin, about that time, the terms positive and negative were used. We'll go ahead and prematurely adopt the positive and negative charge convention. Of course, that implies, among other things, that there are only two kinds of electrical charge, which is far from obvious. One thing that makes it far from obvious is this complication. If you take silk and rub it on a cat, and take a different piece of silk and rub it on a glass rod, you find that the two pieces of silk attract each other. One might be tempted to start inventing new kinds of electrical charge to try to deal with this. Instead, experiment establishes that objects do not always take the same charge. It depends on what they're being rubbed with. So, and you can develop what's called a triboelectric series. Tribo refers to friction. It's some Greek word. Greek word. For example, in this list, if cat skin is rubbed with glass, the cat skin is positive and the glass is negative. But if you rub glass with silk, then the glass is positive and the silk is negative. So glass can have either a positive or a negative charge. So the way this little list works is the object with the smaller number in front of it will adopt the positive charge. And you can see that resin, for most of these things, will be negative, but if you rub it against gutta percha, which is a kind of insulating, it's a kind of rubber, a natural rubber. It's actually used, it was used in early cables, electrical cables, signal cables, and we'll talk about that later. And also for root canals, it's the dentists stuff these things into your down into your jaw if they're giving you a root canal. Of course, gun cotton. It doesn't sound like a good idea, but if you rub resin with gun cotton, the resin will adopt a positive charge. So if you rub resin with gutta percha, what charge does the resin carry? It will be a positive charge since it's higher up on that triboelectric series. Some early experiments were done with balls made of something called pith, and that's just the spongy sort of white material in the rinds of lemons and whatnot. They're easily charged. This material is easily charged, and it's lightweight, so it's easy to see repulsion between them. So uh, if we charge some three pith balls, and we find that 1 and 2 repel each other, and 2 and 3 repel each other, having numbered the pith balls. What can we say? Well, if there are only two kinds of charge, you could 1 and 2 must be the same charge, 2 and 3 must be the same charge, and so that would mean that 1 and 3 would have to be the same charge. So the answer would be C. But that assumes that there are only two kinds of charge. Here's a question that illustrates the importance of experiment in this matter of determining how many charges there are. We have the three pith balls. 1 and 2 attract each other, and 2 and 3 attract each other. What can we say about the charges on the pith balls in this case? Well, if pith ball 1 is positive, 2 must be negative. And now 2 attracts 3, so 3 must be positive. So 1 and 3, one way or another, will have the same charge. So the answer is B, provided that there are only two kinds of charge. You could imagine a universe in which you could have three objects, 1, 2, and 3, and each attracts the other 2. Three mutually attracting objects. Now, it has never been found to happen with objects that are rubbed together. But in fact, the strong force that holds the nuclei together, it does happen. The strong charges, in fact, there are 3 of them, which are sort of arbitrarily called red, green, and blue. If you charge one object with red, the other with green, the other with blue, it turns out that they all attract each other. So the rule is, unlike strong charges attract each other, and since that can happen with three objects, in this case these objects would be called quarks. A red, green, and blue quarks would all 3 attract each other. That kind of situation has never been found to occur with objects that are repelling and attracting due to a thorough rubbing. But even with this, you have to be careful, as we will see here in a minute. But I'll just say that no one has ever found evidence for a third electrical charge. This fellow Stephen Gray was the first person to realize that static electricity could actually be transferred through an object. He used oily thread of some kind, and that he could actually communicate the electricity from its origins to another object. You could almost say he was the first stab at the internet or something like that. But he did not realize that metal was a conductor. But he did discover the existence of substances that will communicate electricity, which we call conductors, and those which do not, which we call insulators. And of course, none of these things are actually not absolutely perfect, so they're in-between type of substances. And nothing is, no substances are true in nature or truly perfectly conducting or perfectly insulating. But that's a general concept that's useful. And again, the main point is that this, the static electricity can flow. Gray found that this is not just something that is a stuff that sticks to an object, but it can in fact apparently flow somewhat like a fluid. Early experiments, like those of Stephen Gray, relied on the principle illustrated here, though the apparatus was seldom this fancy. In fact, Gray was quite poor and did many of his experiments while living in a kind of poorhouse. You know, the idea is simply you've got now conductors. You bring a glass rod up to this metal ball, then the negative charge is attracted to the initially uncharged metal ball, and that leaves, you know, the whole apparatus. If it's initially neutral, then there'll be positive charge remaining, you know, in excess at the bottom, and so you'll get a repulsion. Now, if you actually touch, even though glass is an insulator, if you rub along the metal ball, you can actually transfer some charge, and so that when the glass rod is pulled away, the metal leaves at the bottom are still repelled due to the excess of positive charge. If you're trying to figure out how many charges there is this other complication that neutral objects actually are attracted to and attract charged objects, as illustrated by our feline experimenter. The explanation is to be found in the fact that if you bring an insulator, like that packing material, up to a charged object, then the charged object, the cat here, will attract negative charge in the insulator, and positive charge will be repelled. So you get what's called an electrical dipole. Now, if in fact, as we assume, as is apparently the case, electric force diminishes with distance, then there will be more attraction than repulsion in this case, and so the insulator will in fact stick, you know, be attracted to the charged object, and since it's an insulator, touching the charged object will not have any effect. It'll just stick to the charged object. Nowadays we know that matter is made up of atoms, and so we can let's take a look at it at that level. Cases A and B here are insulators, and the idea then is that a charged object brought up to that insulator, it actually polarizes, it produces an electrical dipole in each individual atom of the insulator. And so you effectively have, in A, you have sort of like a negative charge on the left part of the square insulator and a positive charge on the right part. The charges in between, in some sense, cancel, though there are actually electrical forces that would exist between these objects. Now, C illustrates a conductor. The blue square is a conductor, like a metal. And so if you bring up a charged objects, you actually get more of a true large separation of charge. And so the phenomenon of induced charge works for conductors and non-conductors, as seen here. Here's a demonstration you can easily do. Here they're using a charged balloon to induce charge in the water. I have done this demonstration with success using a plastic comb that has been used to comb dry hair. Here's a drawing of the demonstration. It's important to note that we cannot directly see electrical charges. We can only infer the existence of these charges. So it's somewhat of a theoretical matter, as all physics is, based on experience. Here's a question for you, just to test your understanding. A negatively charged balloon is brought near a neutral conducting sphere. So which of these diagrams most accurately portrays how the charges will appear or exist? I'll give you a moment to think about it. The answer is C. the negative balloon attracts a positive charge and repels negative charge in the sphere. Induction may be also used to produce a net charge. Here is one way of doing that, where you just have two conducting spheres touching, so that when you induce the charge, as seen on the top right, you induce that charge separation. If you make it so that the spheres are no longer touching at that moment, then the left sphere will continue to bear the negative charge, and the right sphere the positive charge. Here is another way of doing it. It turns out the human body, for example, in this case, is a source or a positive or negative charge. So this guy is taking away charge by touching it. Such an object, in this case the human body, is called ground. Sometimes it's literally the earth. But ground is, it can be the fuselage of an airplane. Ground is an object that is large enough so that its own electrical condition is hardly changed by its supplying positive or negative charge to another system. Induction also gives us a way to measure the quantity of charge on an object without disturbing or changing the charge, or the quantity of charge on the object. It works this way, as illustrated by Maxwell. The thread you see there is a non-conductor. The lid is metal, as is the lower container, and it's an electroscope with two metal leaves at the bottom that will move apart if they carry charge. And then there's the ball, which can be either a conductor or non-conductor. The main thing is it carries the charge which we wish to measure. This is what happens when the object is lowered and the lid placed on the container. You get the induced charge as seen here. We're supposing that the little ball is positively charged. Then by induction it leaves a positive charge on the outside of that container, and that includes the metal foils. So the angle between the metal foils at the bottom is a measure of that quantity of charge. Now what makes this apparatus so useful is that, in fact, even if you raise or lower the charged object that you're measuring, it does not change at all the distribution of the positive charge on the outside of the container. We'll talk about why that is so later, but just knowing that it's the case means that now we can easily compare the quantity of charge on two objects without, like we have two different balls. We can just try each one separately and see which one produces the larger angle, and that one has then the most charge. And for example, the apparatus below, which has been modified so you could put two objects in there, if you use, you take two objects, rub them together so that they're each charged, and then you place them inside the charge measuring apparatus, one finds that in fact there is no net exterior charge on this apparatus. So the positive and negative charges of these two objects, which were used to charge each other, are in fact equal in magnitude and opposite in type of charge. Here's another early experiment that confirmed the idea of charge conservation. So you have a charged object, the ball, you put it down in the metal container. It's really not essential that it have a lid. The main thing is that you connect container to another apparatus, E, small metal ball with, again, some foils to detect any charge or change in charge. When you connect it, then some of the positive charge on the outside of the container goes to that apparatus in the lower right, E. Then what happens is this: you first remove the wire connecting the apparatus E to the cup A, which then all the charge that's now on E, which all of it came from the uncharged cup A, so that charge is now trapped on the apparatus E once the wire is removed. Then you remove the charged sphere, and that leaves with the cup with a negative charge, and the quantity of that negative charge is indicated with the metal foils, and the same is true for the quantity of charge on E. And so there on the left we have charged cup A and the apparatus E. When a wire is reattached, both apparati here, the A and E, show zero charge. No evidence of charge remains, demonstrating then conservation of charge. Any positive charge that showed up on E left a deficit of positive charge on A, and so the negative charge of A and the positive charge of E are seen to be equal in magnitude. So that is any charge that's transferred leaves a deficit behind, and charge, using this and other experiments, charge is demonstrated to be conserved. So the conservation of charge was independently discovered by two people. In the United States, we like to talk about Benjamin Franklin, who was a fellow of the Royal Society of, in London. But at the same time, or independently, about the same time, William Watson, a fellow of the Royal Society, did equivalent experiments establishing conservation of charge. And the upshot of this is that that when you take positive charge away from something, it leaves a negative equal charge behind. That suggests that the charge is pre-existing, and that neutrality of an object does not come from an absence of electrical charge, but rather an equality of positive and negative charge. Franklin put it this way: electrical fire is a real element. Electrical fire, I think, is what they call charge then, and that it exists. It's part of matter. It's not created when we rub things together, but it only is one sign or the other is collected. Here's questions that will help you solve a couple of sampling problems. We have three identical metal spheres, and we charge one of them with a charge we'll call Q in quantity. Arbitrary units. We haven't talked about the units for charge, but that's not important. It has a certain quantity that we could measure with the angle between two metal foils by putting it into one of those little buckets that I showed you earlier. So we have a charge Q on the sphere A, and A and B are touched and then separated. How much charge is on sphere B? Because these are identical spheres, there's no reason to believe that A or B would hold a charge different than the other. So when they were touched, we should assume that they shared charge equally. And that would mean that charge B would have charge Q over 2, and sphere A would have a charge Q over 2 remaining. So now we have the situation there in the middle. A and B share equally the charge Q, and that was after they touched. Now, if B and C are made to touch, how much charge will be on the spheres? Well, the total charge of spheres B and C is Q over 2. If they touch, they will share that charge equally. And again, we're using conservation of charge here. So both B and C will have Q, 1/4 of Q charge, and A will continue to have the Q over 2. So now we see after B and C touch, we have A, B, and C have Q over 2, Q over 4, Q over 4 charge, respectively. Now, what if A and B touch again? How much charge is on these spheres? Well, of course, C will keep its Q over 4 charge. A and B together, they have 1/2 plus 1/4, which is 3/4 Q of charge. But they'll share that equally, so 3/4 divided by 2 is 3/8. So it'll be answer D, 3/8 Q. Both A and B will have the charge 3/8 Q after A and B touch. You probably know that that magnetism bears certain similarities to electric charge. One difference, of course, is that a magnet cannot be as easily rid of its magnetic effects as a electrostatically charged piece of glass rod or something. But in fact, you can think of a bar magnet as having 2 poles, and that if you have 2 of these bar magnets, you find that there are poles that repel each other and poles that attract. In fact, that like poles would repel and unlike poles attract. So it's very much like positive and negative charge. We could define, in trying to decide what to call this magnetic charge, we could consider the fact that a bar magnet lines up sort of as seen here with like poles pointing sort of geographically in roughly the same direction or the same pole of the Earth. And we'll call the one that points, the end of the magnet that points north, we'll call that the north pole of the magnet. And the part that points south, we could call the south pole of the magnet. As I mentioned earlier in these slides, William Gilbert studied geomagnetism using a model, globe with a magnet. With that kind of model, given our definitions of north and south poles of a bar magnet, which of these 2 orientations of the bar magnet that represents the Earth's magnetism? All right, so this is not a bar magnet that's being held at the surface. This is a magnet sort of inserted inside this globe to model the Earth's magnetism. Which one of these 2 more accurately portrays the Earth's magnetism, given our definition of north and south magnetic poles? I'll give you a moment to think about it. Consider the fact that like poles repel, unlike poles attract. So, in fact, the pole of the Earth's, sort of magnet, that pretend magnet, that is in the northern extremities of the Earth would be the south pole of a bar magnet. So, the situation there in B is a more accurate model of the Earth's magnetism. Now, magnetism and electricity have a number of similarities. This video demonstrates one of them, that just as we can induce an electric dipole, we can induce electricity, charge separation by induction. You can do something pretty much the same thing in the case of magnetism.
Guys, today I'm going to make a brief video on induced magnetism. Now here I've got a bar magnet, and this is the north pole of the bar magnet, and suspended on this little piece of string here I've got a paper clip. Now the paper clip, this is the north pole here of the bar magnet, A south pole is being induced. Guys, today I'm going to make a brief video on induced magnetism. Now here, I've got a bar magnet, and this is the north pole of the bar magnet. And suspended on this little piece of string here, I've got a paper clip. Now the paper clip, this is the north pole here of the bar magnet. A south pole is being induced in this end here, and therefore this is a north pole here. And I can show you that it must be a north pole because if I take another bar magnet and I go close.
So now those poles weren't labeled. We just were trusting this guy that he's telling us the truth about the poles, and I imagine he is. Experimentally, to verify, determine whether, what are the poles of the bar magnets, the red bar magnets here. You go outside, away from any metallic, ferromagnetic objects, and use the bar magnet to detect the Earth's magnetism. The paper clip, however, if you disconnect it and take it out, unless you've done something like leave it there for hours or increase the temperature of the paper clip, you'll find that the paper clip has minimal magnetism. If it was originally not capable of detecting the Earth's magnetism, unless a great deal of time or a higher temperature is involved, the paper clip is unable to detect the Earth's magnetism after this experiment. There is a difference, however. Let us suppose that we have the situation here that was this guy in the video set up, the north pole, that magnet on top, and the unmagnetized paper clip held by a thread. Well, magnetism is actually induced in the paper clip, as seen here and as he demonstrated. But now what if we go up and touch it, as was demonstrated for electrostatic induction in the other video? There is an important difference, however. In the previous video, the demonstrator was able to give a net charge to an object that had an induced dipole. He did this by touching. So if you have the situation on the far left and then you touch it, as in the middle diagram, what happened with electrical charge is that one of the charges went away or was traveled down the finger, leaving a net charge on the object. But in fact, if the finger's taken, and take a finger away, and you would have then a south pole down there. This has never happened. The paperclip remains unmagnetized, again, unless you induce permanent magnetization by long periods of time or temperature, high temperature. You cannot create by induction a magnet of a single charge, or rather a single polarity. This is the most profound difference between electricity and magnetism. Here's another way you could attempt to isolate a magnetic polarity. You take your bar magnet with the north and south poles, break it in the middle, but instead of getting a left bar magnet with the polarity of south and a right bar magnet with polarity of north, you end up with two bar magnets with equal polarities south and north. And if you keep going, well, you just keep subdividing every time you get both the south and north polarity in equal measure. This is the most profound difference between magnetism and electricity.